Hey guys, today we are going to solve the problem search in a two-dimensional matrix 2. In this problem, we are asked to write an efficient algorithm that searches for a value target in an m by n integer matrix, and we are being told that the matrix has two properties. Each row is sorted in ascending order from left to right, and each column is sorted in ascending order from top to bottom. Okay, that is pretty clear. How can we solve this problem? The brute force way would be to simply have two for loops and iterate over every possible location in the matrix, and every time we are at a certain location ij, ask, is the matrix at this location is the same as target? If yes, we are going to return true. If we didn't find a location in the matrix that holds the value target, we are going to return false. So the complexity of this algorithm is going to be m by n. M by n. Because there are m rows and n columns, and we are going to go over all of the matrix. But of course we can do better than that, because in this solution, we didn't even use the fact that each row and each column is sorted. So what if we were only told that each of the rows is sorted? So let's say we add this given to us, but we didn't have the fact that the columns are sorted. How could we solve this problem then? Well, still, we could have a pretty simple solution. We could iterate over each row and search only inside that row for the value target. And how are we going to search for the value target? We are going to perform a binary search. So this solution would also work. So we would start at the first row and we would check for target equals 5 in this case. We wouldn't find it and we would go to the next row. And then again, we would perform a binary search and we would find 5. So we would return true. The complexity of this solution would be m, because that's the number of rows, times each binary search cost us logarithmic time in the number of columns. So that would be the complexity of this solution, and the space complexity of this solution would be constant. The same applies to the brute force solution. It would also be constant space. Okay, but how can we also use the fact that each of the columns is also sorted? There are many ways to use those two facts. There are also other ways to solve this problem with binary search. But there is another solution that I really like because I think it requires you to think outside of the box. But in the same time, it's not too hard to come up with. So let's clear the board and explain the next solution. Let's look at the following example. In this example, we are looking for the number 20 inside of our matrix. And we can see that 20 is indeed in the matrix. Imagine for a second that you are standing in this matrix and you are beginning from the bottom left. You are seeing the number 7 and you ask yourself, where should I go from here? Well, 7 is smaller than 20. So you know for sure that 20 is not going to be anywhere above you. Why is that? Well, because the columns are sorted. You also know that 20 is not going to be to your left. In this case, it doesn't matter. So the only logical thing to do is to go one square to the right. Now you are looking at 21. And again, ask yourself, is 21 our target? If yes, then of course we find the target. But if not, we know for a fact that 20 cannot be to our right. Why is that? Well, because again, the rows are also sorted. So the only logical thing to do is to go upwards to 9. Now we are at 9, and we see that 20 is bigger than 9. So again, it doesn't make any sense to go up, because target is not going to be there. So we should go to the right. And again, we should go to the right. And now we are 27. 27 is bigger than target, so we know that the target could not be to our right. In this case, it doesn't matter because we are at the edge anyways. and we are going to go up. And now we found target. So as I said, when we are looking at a certain element, we can safely know that it's not going to be above us. So why should we even try to go up? We know that at some point we are going to have to go to the right. So let's go to the right now. This is a kind of a greedy algorithm, and in this case you can see that it works. I think it's pretty clear. What is going to be the time complexity of this one? This solution is much more efficient because at each step we are just going one step to the right or one step to the top. And obviously we are going, the worst case is we are going to end up somehow, it doesn't matter in which kind of route, we are going to end up at the top right. So that in the worst case would be n plus m steps. So the time complexity is going to be linear in n and m. And the space complexity is still constant. There is one more thing I want to explain about this algorithm, and I think it will also help to understand the intuition behind it. So we decided to start from the bottom left. But could we start our traversal over the matrix from the top left, or maybe from the bottom right, or top right? Could we? And the answer is we could start from either the bottom left or the top right. Why is that? Well, again, when we looked at the bottom left, we knew that for sure the answer is somewhere in the matrix. So somewhere above us and somewhere to our right. We knew that there is some type of traversal, that each step we only go to the right or upwards, and if the target exists, then we will get to it. And then when we looked at a certain element, we knew that if it is smaller than the target, then it couldn't be that the target would be present inside of this element's column. So we knew that the answer is going to be somewhere here. And for that reason, we knew that we can go to the right and still have some type of boundaries that the target is going to be inside of them if it exists in the original matrix. So at every step, we kind of cornered the target that we want to find. But what about if we didn't start from the bottom left, but instead we started from the top left? So we would have the same property in the beginning. We would know that, okay, in the beginning, the target, if it's in the matrix, is going to be inside of the boundaries that we'll begin with. But what about now? If we compare one to the target, we are going to see target is bigger. But we have no idea if we should go to the right or if we should go down. Because both the rows and the columns are sorted in ascending order. So if 20 is bigger, it could be both to our right or to our left. So for example, in this case, 20 could be here. And if 20 is right here, then we must go to the right. We can't go to the downwards. But if 20 was here, then we had to go downwards and we couldn't go to the right because then we would eliminate 20 because we would only look at this part. And why is that the case? Because when we start from the top left or from the bottom right, both the rows and the columns are sorted in the same manner. In contrast, when we looked at the bottom left, or if we have looked at the top right, then on the one end, the rows are sorted in ascending order, if we are from the bottom left, and the columns are sorted in decreasing order. So we had like two options. Either target is bigger than us, and then we would want to increase the current value, so we could for sure go right, or target was smaller than us, and then we wanted to decrease the current value, and we could go up. I hope it's clear now. So this is both explaining why you can start from two of the other corners, and also I think it kind of explains the intuition, because this is kind of what helped me to solve this problem. And now let's move on to the code. The code is extremely simple, I promise, so just hang tight and we are getting over it soon. Okay, so as we said, we are going to start at the bottom left of the matrix. And now we want, while we are in bounds, to every time ask if the current element we are looking at equals to target. If yes, then of course we found the target. If not, then we're going to ask, is the target smaller than us? In the last case is when the target is bigger. And if we didn't find the target while traversing the matrix, then we know that it's not there. So this should do. As you can see, it works. By the way, I will mention one thing which is kind of funny. The solution is actually practically, at least in the test cases that we are given by Leetcode, less efficient than the solution that the second solution that we talk about. I will just show it for fun, but one solution that we said is we could traverse all of the rows and for each row we could have a binary search. So we will have to write some function that performs binary search. So the binary search function will return us true if the row in the matrix, if the specific row in the matrix has target in it. So what we are doing is for each row in the matrix, we are going to run binary search to check if the target is inside that row. And if we didn't find target in any of the rows, then we are going to return false. And as you can see, it works, and it's actually, yes, slightly faster, but this is the better solution. In a job interview, it's always good to give out all of the solutions that you have. So every solution you have and it's working, then it's worth pointing out. So in an interview, I would for sure talk about the brute force approach. Of course, you would only talk about it for maybe 10 seconds. And then I would actually also explain this solution. And I would maybe say that if only the rows were sorted, then I would use these solutions. If only the columns were sorted, then of course you could do the same solution, but on the columns. And yeah, so as I said, this solution runs in m times log n. And you could also do the same solution for the columns. So you could do n times log m. And we also have the more efficient solution, at least by the time complexity, that runs, it's here, that runs in n plus m, which is the best solution for this problem. As I pointed out, there are a few more solutions, but I think it's too much for one video. And they are also a bit more complicated and not as good. And there are solutions that use both the fact the rows are sorted and the fact the columns are sorted, but they are actually not really better than this solution. They have different time complexity, but not necessarily better. And that's it, guys. I hope it's clear, and I hope you enjoyed, and see you next time.